Welcome everybody. It's a pleasure to have here Alessandro Lupi as a guest of our seminar space. So Alessandro, a brief history. Alessandro got his degree in Milan, then his PhD at the University of Insubria in Como with Francesco Ar. Later on, he moved to Paris for the first postdoc at the IAP, working mostly with Marta Volonteri, and then he's been kind of a traveler. He came back to Italy at the Normale di Pisa for another postdoc of a couple of years during the COVID years, I remember, working with Ferrara. Then he moved back to the north of Italy, Milano again, and in the end, finally, he got RTD B position at the Insubria University, where he is based now. So thanks for accepting our invitation today. He's a theoretician, he's an expert of simulation. So anybody who's interested on this matter, please come to my office wherever you stay and talk to him if you want after the seminar in the early afternoon, let's say. And so today is going to talk about the exciting matter.
Thanks, Francesco, for the introduction and for inviting me here. It's a pleasure to be here to give this seminar. As Francesco said, I'm a theoretical astrophysicist, mostly using simulations. I work on different topics, and everywhere in my research, I treat hydrodynamics. And in this case, I'm studying how the hydrodynamics, especially in the context of cosmic structure formation, impacts the formation and evolution of black holes, which is one of my main lines of research. And this work has been done in collaboration, in collaboration with some of the people, all the people here, plus other collaborators, and also Francesco is one of them, although it is not mentioned here. Okay. No. Ahead. Wait a moment. Okay. Yes. Okay. So first of all, a brief introduction. We know that black holes exist in two main populations: a population of stellar mass black holes that we know that form at the end of the life of massive stars, and we have observed them, especially in binaries, X-ray binaries, and also thanks to the gravitational wave detections by LIGO Virgo, now we have detected them when they merge in black hole binaries. And we have found that typically at masses around 10 up to 100 solar masses, and they occupy this part of this mass diagram. Then we have a dearth of black holes in this region between 10 to the 2, sort of up to 10 to the 4, and then we have this big bulk of population of black holes that are supermassive, between 10 to the 4 to the 5 up to 10 to the 10, and they typically live in the center of galaxies. And while for the stellar mass black holes, we know that they form at the end of stellar evolution, for the massive black holes, we don't know yet how they form and how they evolve. And one of the problems is that we observe them when they are very massive. So unless they form with this mass already from the beginning, they have to grow to this mass, starting from a lower initial mass. And in this respect, if we take the evolution of the luminosity, the AGN luminosity function, and the Soltan's arguments that tells us that black holes gain most of their mass by gas accretion, we can speculate that this black hole formed with a lower mass, with the initial masses between 100 and 10 to the 4-ish as seeds, and then they grew via mainly gas accretion, but also maybe via mergers with other black holes, or one of the recent ideas is that they could also capture stars and grow by tidal disruption events. The point is, we don't observe any black holes here, so for some reasons, these seeds have grown without leaving any trace of their presence in this mass interval. Today, many models have been proposed to explain this formation. Historically, we can split them into light seeds, heavy seeds, and medium seeds, depending on their mass. At the beginning, these classes have been investigated separately, but I like to think that maybe they are simply the result of different environmental conditions that lead to a slightly different mass. In particular, for the light seeds, these black holes could form with masses around 10 to the 2, 10 to the 3 as POP3 remnants. So in the first halos that form in the universe, you can see here a sketch by from a review by Marta in 2012. If we have the first dark matter halo and gas collapsing, there could be some fragmentation and form a POP3 remnants. Then another possibility is that there is almost no fragmentation. The gas becomes globally unstable and collapses into a center almost monolithically. We form a supermassive star, the core collapses and forms a black hole, and we form a quasi-star, and then the black hole accretes all the envelope of the star, reaching masses between 10 to the 3 and 10 to the 5. Of course, the range is quite large, and the reason is that different details in the physics, also in the radiation transport, during the formation of this object can lead to different masses, and there is no consensus about the final mass yet. Or another possibility is that we form, because of fragmentation, we form a cluster of stars, and if the cluster is dense enough, these stars can collide and form more massive objects, and in the end, we form a medium seed with a mass around 10 to the 3 or maybe larger. It depends also in the case on the physics involved. If these protostars, before merging, accrete gas, they might become even more massive and larger, and so they end up, the final mass could be also 10 to the 4 or 10 to the 5, as some recent papers suggest. And the point now is, we would like to understand if all these mechanisms are plausible, if there is an effect, if they are a manifestation of different environmental conditions or not, and how relevant these different channels are in our universe for the formation of these massive black holes. One of the main ideas to test these different channels is to look at two different populations of cosmic structures. The first one is to look at massive galaxies, in particular quasar host, especially because they are very active galaxies. We can observe them up to redshift 6 or 7. These are results from a few years ago, but now with JWST, we're observing even more objects. And you can see that if we trace back their initial mass, assuming a constant accretion rate at the Eddington luminosity or half Eddington, the initial mass around redshift 35, when the first stars start to form, is quite different. It can range from a few hundred, if it's constant accreting at the Eddington limit, up to 10 to the 4, 10 to the 5, or 10 to the 6. And this is a problem also for the heavy seed formation mechanism. Okay. And another problem with this is that we observe these black holes when they are already massive, so we don't know what is their initial mass. Okay. There is a huge interval here, and it's hard to constrain if we only observe these objects. We should be able to go back to higher redshift to observe when they form. Okay. And on the right, you can see the result of a simulation that I performed. I'll discuss a bit later, where I try to reproduce these objects starting from a reasonably massive black hole. And you can see the growth of this black hole, the comparison with two most massive quasars observed up to a few years ago, and the evolution of the Eddington accretion rate in blue. Another possibility is to look at dwarf galaxies. Especially, dwarf galaxies can be observed at low redshift, because when we go to high redshift, it's harder and harder. And the advantage is that in dwarf galaxies, the black holes are expected to be small. If the density of gas is low, they struggle to accrete, so they keep memory of the initial mass. There are a lot of dwarf galaxies in the universe if we think about the galaxy luminosity function. The problem is that if these black holes accrete a low amount of mass, they are potentially quiescent and not very active, so it's hard to detect them. And so we have to find different mechanisms to detect these objects. Okay. And another problem that some people suggested is that since they have a low mass and the potential well is shallow, these black holes might wander around the center of the galaxy, especially if the profile is scored at the center, and so they would struggle even more at accreting. And so this would be a problem for the detection. So if we want to study this object, the first thing we can do, as I said, is to look at massive galaxies. So what we have tried to do in the last year is to try to constrain the different mechanisms in the progenitors of quasar-host galaxies. Some works have suggested that these heavy seeds, for instance, occur via two main scenarios. The main one is the so-called pair synchronization. So we have two halos, one of them forms stars. These massive stars produce a lot of Lyman-Werner radiation. Lyman-Werner radiation impinges on this halo, and because of this strong Lyman-Werner flux, H2 cannot form. H2 is the main source of low temperature cooling in galaxies, and trigger fragmentation that leads to the formation of low mass stars. So if we can remove H2, we can allow the gas to cool by atomic cooling only, so at 10 to the 4 Kelvin, and we can reach monolithic collapse of an entire cloud without fragmentation. So if we can provide this source of radiation, we can form heavy clouds that form a massive seed. Recently, WISE proposed an additional mechanism, which is based on the fact that in some galaxies, especially at high redshift, the growth of the galaxy itself, the accretion of matter from the filaments and from the gas around, from the region around galaxies, can provide an additional heating mechanism, dynamical heating due to mass accretion. And if this dynamical heating balances the cooling provided by the formation of H2, we can suppress H2 formation and reach the same conditions of this pair synchronization without the need for a Lyman-Werner radiation. So they proposed this idea, testing it with some simulations, and they find that in some cases it's plausible. So what we try to do in our work was to put together these two mechanisms and to see how relevant they are in the formation of the first seeds in quasar-host progenitors. To do this, we started from a cosmological zoom-in simulation of a massive galaxy at redshift 6 with a resolution of a few tens of parsec. It's a dark matter-only simulation. This you can see the equivalent with baryonic physics, but for this study, we neglected baryon, and we only focused on dark matter. And then, and the advantage of this simulation is that we can solve the transition from the mini halo phase, with the virial temperature of the halo below 10 to the 4 Kelvin, to the atomic cooling phase, which is exactly when the suppression of H2 formation is important to provide the condition for heavy seed formation. And we built the semi-analytic framework to test this idea. We incorporated all the details known to date about this dynamical heating and pair synchronization mechanism in this semi-analytic framework, and we ran this semi-analytic model to test the conditions for the formation of the heavy seed. I'm not entering into the details now, but if you are interested, we can discuss offline about all the physical details that are in the model. And you can see here the result. On the right, you can see the large-scale structure around the halo. The yellow part here is the main halo, and the color map corresponds to the Lyman-Werner radiation that is self-consistently computed from all the halos that form stars during in this semi-analytic model. And you can see that in the center, the flux is extremely high because there is a lot of star formation. So one might say, naively, that since there is a large flux, it's easy to form heavy seeds in this case. And the answer is no, because there is another problem that we have to take into account: metal pollution. When we form a lot of stars and the stars evolve, they inject metals. And when metals are produced, cooling to low temperature can be provided by metals instead of H2, and fragmentation can occur also due to metals. And while H2 can be dissociated by Lyman-Werner radiation, for metals, there is no solution. Metals cool down the gas to very low temperature quite easily, and so it's impossible to collect a large mass inside the halo without fragmentation. And so when we put together all these two effects, Lyman-Werner radiation, metal pollution, we find that in the end, we only form a few objects that could lead to the formation of heavy seeds. You can see here the numbers in our region of dynamically heated halos, those halos that reach the atomic cooling threshold by accreting fast, accreting a lot of material in a short time, which are quite a lot, so more than 10 to the 4. So in principle, this could be all seed target halos for heavy seed formation. But then if we look at the atomic cooling halos that also have nearby sources of radiation, only 27 are present. So if we rely on the synchronized pair scenario, only a few of them can actually form a heavy seed. Then we can also put another constraint. We say, okay, but we want these halos to be pristine, because if there are metals, we have fragmentation. And in this case, you go down by a factor of 3 in the dynamically heated halos, and you go to 2 for the synchronized pairs. So despite the region is overdense, there are a lot of galaxies forming, and so potentially there could be a lot of halos where direct heavy seeds could form. In the end, if we take these conservative mechanisms of the synchronized pairs, only 2 sources, only 2 halos can lead to the heavy seed. And you can see that they form at quite high redshift, between redshift 10 and 24. The filled circles correspond to the pristine halos, these 2 halos, and the gray ones are all the synchronized pairs that we found. This is the typical redshift where other studies of direct collapse black holes suggest they would form. And this could be a problem, because if we go back to the distribution of massive at high redshift, this is too late to accrete them, even with an Eddington limit growth, to explain 10 to the 9, 10 to the 10 solar masses at high redshift. So it's still hard. Then we have to take into account another effect, that this region is not the quasar progenitor only. It's also the environment of the quasar progenitor. So if we can put another constraint and ask ourselves, how many of these halos end up in the main galaxy by redshift 6? So how many of these could actually be the seed of the quasar that we observe at high redshift? And if we consider these, we go down to by a factor of 3, or even considering metal polluted ones, and from 27 to 9. And then if we also require for the pristine gas, we go down by another factor of 3 here, and here we reach only 1. So there is one candidate, which is good, but in the end, even if this region, in principle, would be more likely to have a large number of heavy seed black hole, in the end, the effect of metal pollution suppresses this effect. And so in the end, if we are lucky, we can have 1. If we are not, Poisson noise, so this could be 0, which means heavy seeds in these regions could still be hard to form, according to this model. A nice thing that we also found in these studies, that if we measure the Lyman-Werner flux distribution in all the halos here, we can find that it peaks around a few hundred. The typical requirement for the heavy seed from other studies is around 10 to the 3. Okay, so all halos above 10 to the 3 might be likely to form a heavy seed. But of course, if we look at the pristine ones without metal pollution, you see that only one, which is this one, reaches 10 to the 3, and most of them are below this threshold. Of course, one might relax the condition and say that maybe above a few hundred, even if it's not exactly the threshold, we might still suppress enough H2 to get enough mass, maybe not for a 10 to the 4, 10 to the 5 solar mass black hole, but maybe for a few 10 to the 3 solar mass black hole. So in this case, we might still have a reasonable number of objects. Of course, it has to be tested in a more complete simulation, and this is what we would like to do in the future. But for now, this is what we can say. And so overdense regions where quasar hosts form might be more prone to have a large number of synchronized pairs and highly accreting objects. But in the end, because of the large star formation rate in this region, only a few candidates might lead to the heavy seed formation. So we have not solved the problem, even in high redshift quasars.
Alessandro, can I ask you?
Yes.
I think I missed at the beginning how you define the overdensity regions. So how these results depends on how you choose your overdensity level, or?
Well, this has been chosen as a region which correspond more or less to what we expect from observations of high redshift quasars. So we took what we did was to create initial conditions for a massive halo that simulations suggest to be the typical host of quasars, around above a few 10 to the 12 solar masses at redshift 6. And then we ran different simulation, and with a simple semi-analytic prescription, we checked the galaxy overdensity and compared it with the Subaru results by redshift 4, which at the time was the only available one. And we found the one that was more or less consistent with the results found by Subaru. So we tried to reproduce more or less the typical halo of a quasar host to test this model. Of course, we have other two cases that we have not tested yet, one for a less dense region and one for an even denser region. But of course, it takes time to run, and so we have not done it yet, but maybe in the near future. So this is the main result. Of course, this can tell us that maybe one of these object forms. So it's a good news. However, as I said, their subsequent evolution is still uncertain because it depends strongly on how galaxies form and evolve in the universe. And I will talk about this a bit later. Of course, if we want to improve this description, now we have to include proper fluid dynamics in the simulations. And what we can do is to study the same system, also including the evolution, fluid dynamics, the formation of stars, black holes, and the evolution of black holes in numerical simulations. However, if we want to study the formation of low mass black holes, we have some problems. Ideally, what one would like to do is, okay, we take cosmological evolution typical numerical simulations of cosmic structural formation have 10 to the 4 solar masses for the dark matter particles, 10 to the 3, 10 to the 2 solar masses for baryons, which is okay for most studies. Then we have to include gas cooling, and typically people use cooling tables. So we compute the cooling rate as a function of temperature and density, and then we compute how the gas cools down. We include star formation, typically is done in an IMF average way. So each stellar particle that forms in the simulation is a stellar population with an IMF. And then we compute the feedback of these stars and how this feedback affects the gas and the formation of the galaxy. And then we include black holes, maybe including different formation mechanisms, but because of the resolution, most people say, we assume heavy seed formation and we neglect the rest. But if we want to study how these black holes form, we have to move forward and to include all the different scenarios. Then people include accretion feedback, and feedback may be mergers. And as I said, of course, we would like to have black hole masses that range from 10 to the 2 to 10 to the 4-ish to cover the entire range of black hole seed formation masses. What is the problem? That since the black hole mass is typically lower than the dark matter mass or the stellar mass of the simulation, if we study the dynamics of this black hole mass, even if we try to correct it as Tremel suggested, the dynamics is not very well resolved. So you can see here that the blue line is without correction for the dynamical orbital decay due to dynamical friction of black holes in galaxies. And when the black hole is 10 times more massive than the dark matter, you can see that there is a lot of scattering. If we correct for this, you can see the orbital decay very well, and then it settles at the center of the system. But if the ratio between the dark matter mass and the black hole mass is 1, you can see that the picture is not very clear. There is a lot of scattering anyway. Of course, you can see a trend, but it's not very accurate. So this is especially a problem because when black holes have a low mass, especially in dwarf galaxies, but the quasar progenitors are still dwarf galaxies at very high redshift, but still dwarf galaxies. If they wander around the center because you don't resolve the dynamics, then your conclusions will be wrong. Okay. But not because the black holes are actually wandering, but because you're not able to resolve the orbital decay very well. So you might speculate that they are wandering, so they are not accreting, but it's not what actually happens.
The center of the yellow.
Yes.
Okay.
The galaxy that forms. Okay. So this is the yes.
Looks like on the left you are also more far away from the center, even though your black hole is more massive than the matter particle. Why is that? Shouldn't you expect?
But these were simply tests of isolated system by Pfister, just to show what you would get when the mass ratio changes. So this is telling you that when the black hole and the dark has a mass comparable to the dark matter or the stellar mass of your simulation, even with subgrid corrections to the orbital decay, your dynamics is not very accurate. And so you have to find another solution to correct for this. And this is what I'm gonna show you. Of course, if we want to resolve this in a better way, we have to increase the resolution. This is the simplest solution we have. So we would ideally, we would like to go to 100 solar masses per dark matter particle, which is lower than the typical mass of a black hole seed forming, either from pop-3 stars or intermediate or heavy seed mechanism. And in this way, we could resolve the black hole dynamics. We would like to continue to have the cosmological evolution, to have gas accretion and the formation of the structure. But the problem now is that if this is the mass resolution for dark matter, star formation cannot be modeled as an IMF average quantity. So you have to treat single stars, at least the massive ones that provide feedback. And so we have to change the star formation prescription. You have to change the stellar feedback, including wind, supernovae, and also radiation. And then, of course, since we want to follow almost pristine gas for the formation of first stars and black hole, you have to follow gas cooling in a very accurate way, not with cooling tables. So you have to include H2 that forms out of equilibrium. So we need on-the-fly chemistry, and the stellar radiation affect abundances because of photochemistry that has to be coupled together in the simulation. And then again, we need black hole accretion and feedback. And of course, if there is accretion onto low mass black holes, the peak of the emission of black holes of the accretion spectrum is in the X-rays. So we need an appropriate radiation spectrum and also X-ray chemistry, which is quite complex because of secondary ionization and secondary heating from fast electrons. So all of these has to be put together, and this is what we've tried to do. We have run a zoom-in cosmological simulation of a dwarf galaxy at redshift 6 for the moment, and in the future we would like to apply this model to the progenitors of a quasar host, including also all the different scenarios for black hole formation. The halo is 210 to the 9 by redshift 6, and the mass resolution for baryons is 35 solar masses. We are using Chrome to follow the chemistry with a very accurate model that we published in 2020, and that has been updated, including all these species that are mainly responsible for cooling also in the low metallicity gas, photochemistry, and X-ray chemistry. We include star formation, and since we start from metal pristine gas, we cannot model the typical IMF of POP2 and POP1, but also POP3 stars. And so following Stacy in 2016, we include POP3 star formation between 10 and 1,000 solar masses. Since our resolution is not enough to follow the formation of the protostellar core, we have devised a detailed model where when the star that we want to form as a mass which is lower than the resolution of our simulation, we extract some mass from the gas element and we form a star, and we leave the rest of the mass of the gas there. If instead the stellar mass is larger than the gas mass, in order not to abruptly force the IMF to be truncated, we account for sink formation. So we convert the gas particle into a sink, and then we accrete nearby gas particles in order to reach the mass of the star we want to sample. Okay. And with this model, we have tested in the collapse of an isolated halo. You can see here how we can reproduce the IMF. This is for the POP3 stars between 10 and 1,000, and this is for the POP2 and POP1. You can see a peak here, and the reason here is that since the low mass stars in the typical IMF are forming a very large number, and in order to avoid to slow down the simulation, what we've done is to assume that all stars will be below 8 solar masses, instead of being treated one by one, are treated as a single star with, well, in this case, it was tested with 4.5 solar masses, but now in the fiducial simulation is 3 solar masses. So we don't expect it to affect the dynamics too much of the more massive objects. And then we include stellar feedback, including also the evolution of the Sedov-Taylor and the momentum conserving phase during supernovae. We include winds extracted from very recent models of stellar evolution from Parsec and Nomoto for the POP3 stars. We include black body spectrum for the radiation of single stars for POP2 and POP3, and the stellar evolution accounting for black hole formation at the end of stellar evolution with remnants above 3 solar masses. Then we include, for the moment, POP3 remnants only, and in the future, we want to include also the other two scenarios. For the moment, we're assuming Eddington limited accretion, a kinetic wind feedback when radiation couples with the nearby gas, radiative feedback with the black body, plus a corona, and black hole mergers. We've put all of these together in a simulation that took a few months to run, and this movie is the result of our simulation. You can see the formation of the first core of the halo. You can see it's not collapsing yet. Now the first dense region is starting to form, the first star forms. You can see the effect of supernovae. The black dots are black holes, and the green one are stars. At some point, you might notice here a clump forming, a star that forms and then disappears, and this star is a peri-instability supernova. So stars between 120 and 260 solar masses, when they evolve, they explode as peri-instability supernova, so they completely disappear. So you might see a bubble expanding and the supernova disappearing, the star disappearing completely. And you can see these are the, sorry, I run it again. These are the stars that form in the system. On the right, you can see a map of the virial radius shown in with the red circle of the system. The blue one is the central kiloparsec of the system, and you can see the distribution of stars and black holes inside this galaxy. And you can see that many of them are at the center of the system, within the central kiloparsec. Okay. Now, if you notice here, these will be you see the peri-instability supernova, the star has completely disappeared, leaving no remnant at all. Okay. Now, if you look more quantitatively at what happens, you can see the evolution in mass as a function of redshift of the stellar distribution in green and of the black hole distribution in blue. And you can see that because of the POP3 star formation that we have and the formation of very massive black holes around a few hundred solar masses, you can see that most of the mass in the system by redshift 6 in this dwarf is in black holes and not in stars. Okay. So 10 times more black holes than stars are in this galaxy. Of course, as time passes in the future, this galaxy might grow more stars because it has been metal enriched. So the star formation will occur mainly as POP2 and POP1 star formation, so dominated by low mass stars. And so the stellar mass, the ratio will change very quickly to a typical system that we observe nowadays. But at this redshift, with these very low mass galaxies, most of the objects are POP3 remnants. Okay, and you can see on the right the mass distribution as a function as a function of redshift of the black holes that form in the system. And you can see two bulks here, two regions. You can see the horizontal lines correspond to the black hole mass. There is almost no accretion in this system because the mass is still low. But in a more massive object, we could also find accretion by these black holes. And they form with some mass at some point, and then they keep the same mass, more or less, over the entire evolution. You can see in some cases these jumps are mergers, because sometimes in the same cloud we form two nearby black holes, and because of the subgrid prescription we have, they quickly merge. Okay, we are not following the inspiral and the shrinking of the binary, so this is for the future, but we can see some mergers, and you can see that this population of black holes is dominated by more metal-rich objects, where the IMF stops around 100 solar masses, but there is a bulk of POP3 remnants with masses between a few hundred and a few of them also above 1,000, which are the results of the merger of 2 or 3 nearby black holes. So you can see that also with POP3 stars, according to our model, we could form black holes that are reasonably massive, and so maybe comparable to the low mass end of the heavy C formation or the medium weight scenario. Okay, this is still preliminary. We are working on the analysis now, so stay tuned for this. But now, since my talk is also about the evolution of this object, let's forget a bit how these black holes form, and try to see what happens later, because this is extremely important also in the light of new observations. We know that at low redshift, black holes and their galaxies show some correlations, and one of the main questions is how these correlations are established and how they are connected to the high redshift universe. So there are some ideas where one of them is that if the relation, even if the relation is not in place at high redshift, the black hole might grow first and then the galaxy catches up, or the other way around, the galaxy grows first and the black hole catches up, or they grow in symbiosis. And there is no consensus about this, and new observations at high redshift try to see if these correlations are already in place. If we look at quasar hosts at high redshift in particular, in the past, most of them have been selected in optical band, where the luminosity is dominated by the black hole, and there is a lot of dust obscuration. So with this observation, we could only probe the black hole itself, but not the galaxy host. And if we want to measure the correlation, we need the properties of the galaxy host. But recently, thanks to ALMA, and now also to JWST, we have started to collect information on the molecular gas, on the gas distribution in this quasar host. Especially in the far infrared with ALMA, we know that there is no attenuation by dust, and the AGN contribution is subdominant, so we can actually probe the gas very well. And with JWST, with the Resprem optical lines and the emission of the stellar light that are in the optical are less affected by dust attenuation, we can probe the stellar distribution of this object. And you can see here a recent paper by Yang et al., where I was also involved, of the first detection of host galaxy with JWST. Here you can see some results by Roberto's work from 2018, where he measured, thanks to ALMA, what is the typical C+ luminosity and the star formation rate of these quasar hosts. And they found that these galaxies were already rich in dust and molecular gas, so we would expect them to be very well evolved galaxies. And with a quite large mass, the estimation of the dynamical mass showed galaxies above 10 to the 10 solar masses. So these are really massive objects at very high redshift. And so this might be a problem for our cosmic structure formation model. And recently with JWST, people have started to populate also the black holes stellar mass correlation. You can see here the results by Maiolino for the black hole stellar mass correlation from JWST. You can see that compared to the local AGN population here, they are typically overmassive. These are the two quasars of the Yang paper that I mentioned just a moment ago. But if we look at the dynamical mass instead of the stellar mass, so that accounts for all the mass in the galaxy, you can see that they not differ very much from the correlation at low redshift. In this case, you can see that this is mainly from Cormendier-Ho, so dominated by massive galaxies, elliptical galaxies at low redshift. Of course, these two populations are not the same, And indeed, if we put them together, you can see that this population lies down here. So these black holes might still look overmassive compared to the local AGN population. And this is the same Roberto found with the measuring the dynamical mass using ALMA, that these black holes look at the mass ratio of around 10 to the -2, while the local AGN population is here. So we tried to constrain this using our simulation to see if our model can find the same result. And we did this using cosmological hydrodynamical simulation of a massive halo at redshift 6, including a very detailed model for the ISM and the H2 chemistry. You can see here the properties of the simulation. We have a very high resolution. We can resolve structure down to a few parsec in the center of the galaxy. The resolution a bit worse for the dark matter distribution and the star, but still around tens of parsec. We have included many state-of-the-art models for star formation, supernova feedback, winds, stellar radiation, and black holes. And we have found that these galaxies at redshift 6 or 7 already have a very well-defined disk with spiral arms. You can see the stellar distribution here, face on and edge on, with the central black hole here in red, and the gas distribution, the H2 distribution, and the C+ luminosity inferred from the gas properties. And you can see that the very nice disk is already in place at this redshift. And this is consistent with what the measures via ALMA and also now in JWST suggest, that these galaxies are already evolved. The potential well is very deep, and so a disk can remain there without being subject to strong perturbation by supernova. So disks were already in place when the universe was only 1 gigayear old. And our simulation, thanks to the exquisite resolution we have, can reproduce this very well, both in the stellar and the gas distribution. If we look more quantitatively at the evolution of this system, you can see here the evolution of these different quantities, the stellar mass, the gas mass, the halo mass. And in red, you can see what we would have inferred for the stellar mass if we have used the the calibrated UV stellar mass relation, used that calibrated at low redshift. And you can see that they kind of agree when the galaxy is very massive, but when you look at low mass galaxies, the bursty star formation occurring in this system makes this estimate quite different from the actual stellar mass. And this has been also shown in a recent paper by the fine collaboration, that the bursty star formation might make galaxies appear more luminous than what they are in reality. And this is due to the bursty star formation that you can see here. When the galaxy is still growing in mass before it reaches 10 to the 10 solar masses, the bursty star formation here can affect significantly the emission and our estimates from observations. If we compare our estimate from the simulation for the star formation rate, we found them in agreement with the estimate also by De Carli and also with recent results by GWST. They are very massive galaxies with high star formation rates in the order of 300, 800 solar masses per year. They are very well evolved and metal-rich, as observations suggested, and indeed we have 1-2 solar metallicity for this galaxy. And you can see the black hole evolution in this system. And you can see that there is an initial phase where the black hole is not growing, that I dubbed phase 1, one where the black hole is growing at the Eddington limit, and one where the black hole is self-regulating. So our black hole is slightly less massive than the most massive one observed, but not very far away. And these three phases correspond to the phase where supernova feedback is very powerful and steers the gas around the black hole, suppressing its growth. But then when the gas available in the center becomes significant, supernova effect is suppressed, and so the black hole starts growing at the Eddington limit almost constantly, until its mass becomes large enough for its feedback to start regulating the accretion onto the black hole itself, and so the black hole slows down its growth. If we put this in the context of the correlations, you can see in blue the evolution of the black hole and the stellar mass compared with the local AGNs in red and the giant ellipticals at low redshift in green. So you can see that this black hole looks overmassive compared to the local AGN population, but in our simulation, if we compare it with the giant ellipticals, is in the bulk of the population. Of course, this might be a case where the black hole is not growing very fast, so some observations suggest also objects around here, but it's one simulation and already expensive, so we don't know if more exotic objects could explain this population. But we also tested whether the estimate of the dynamical mass from observation could affect the position, the location of the object in observation. So we try to follow the same approach using observation. So we estimated the C+ luminosity, and we try to infer from the properties of our galaxy what observation would have suggested. And you can see that compared to the actual measure in purple here for the mass sigma relation, if we use the gas to estimate the dynamical mass, our galaxy moves out of the correlation. So the estimate of the dynamical mass might introduce a bias in the measure, especially if we use gas. If instead we use stars in red, it lies on the relation. And this is also what new JWST results from Maiolino suggest, that for the mass sigma relation, the black holes are consistent using the stellar distribution. And the same for the dynamical mass, black hole mass, stellar mass. Here I showed the ratio, and you can see the comparison with the Carly and our simulation using different estimates for the dynamical mass and how the results move along this in this diagram. Of course, new results are by JWST are suggesting now that this overmassive black hole here in the upper end of this distribution might actually exist, and so this problem is not being solved, but more data is needed because, of course, because of the lower bias, we are simply observing the most active objects that may be accreted faster than the others. Yes, but I'm almost done. So we have started wondering how we could explain this, and what we've come up is that maybe there is a phase of super Eddington accretion that we didn't model in our simulations that can allow the black hole to grow faster. So what we've tried to do is to update our simulation from 2019. Now we have more accurate models of metal chemistry with on-the-fly radiation transport, and we have removed the Eddington limit constraint from the simulation. So we are allowing our black holes to grow above the Eddington limit, but accounting for a proper feedback during the Eddington accreting, the super Eddington accreting phase. Starting from my previous work and also work done in collaboration with John Regan, we have implemented the super Eddington accretion phase where when the black hole is accreting above the Eddington limit, GR radiation hydrodynamic simulation suggests that strong outflows are produced in the form of jets, and despite the radiation efficiency goes down because of photon trapping, there is still a lot of radiation coming out, saturating at about a few Eddington in luminosity. So we are modeling these by injecting a jet. You can see this is the black hole and the gas around the black hole, which is kicked along the direction of the angular momentum around the black hole, perpendicular to the accretion disk plane, in the form of jet with a high efficiency and radiation. When the black hole is accreting at lower Eddington ratios, we have a wind plus radiation, so you have an opening angle which is around 45 degrees, a semi-opening angle, which is what we expect from broad absorption line winds. And when we go below 10 to the 3, 10 to the minus 3 in Eddington ratio, we enter the ADAF regime, and in this case, we are modeling again the production of a jet plus some radiation, despite the efficiency goes down. And we have tried to include this to see if super Eddington phases are plausible. This is a collection by Marta, where she put all the simulations to date of GR, MHD, accretion disk, and you can see that there is not a lot of consensus about the efficiency of the radiation emitted from the disk. You can see this is the slim disk model, the continuous lines here, the Abramovitz model for slim disk with photon trapping, but you can see that simulations are all over the place here. So there is no consensus. And for the kinetic energy, you can see that still, again, here, there is a large scatter. So it's not clear how super Eddington has to be actually included in simulations. We have tried to make something reasonable, but we need more studies on accretion disk scales to see how this occurs in reality. And we have tested two different models, one in which we assume that the accretion rate above the Eddington limit produces a jet in the so-called magnetically arrested disk configuration. So when the magnetic field is strong enough, it stops, it determines the dynamics of the accretion in the central region, and the efficiency of the jet is extremely high. And you can see what we found for the evolution of our quasar-host galaxy in this plot for two cases. One is the one with the magnetically arrested disk configuration, and one in which decided that since the spin of the black hole in the simulation for the moment is kept fixed, maybe there is some diffusion of the magnetic field, and so we don't reach the magnetically arrested disk regime, but we stop at half the magnetic field flux. This is a fudge factor that we included to suppress a bit the efficiency of the feedback. It's not at all constrained by simulations because, as I told you, they are all over the place. And we have tried to investigate what is the difference in the growth of the black hole and in the properties of the galaxy. You can see this is the same simulation run down to redshift 9.5, and at some point when the black hole has formed, we stop the simulation and we split the simulation in two equivalent simulations, one with the more efficient jet and the one with the less efficient jet. You can see that if we look at the stellar mass in yellow, the total gas mass in red, the difference is very mild, less than a factor of 2 in the property by redshift 7.6. If we look at the evolution of the H2 mass, which is the most important for star formation, there are some differences in some phases that are associated to the different growth of this black hole in the two simulations. And if we look at the two cases, we can see that with the MED, the black hole, starting from 10 to the 5, apart from this phase, then there is a super Eddington accreting phase, and the black hole almost very quickly self-regulates itself, and it slows down its accretion before reaching 10 to the 7 solar masses. And this is redshift 7.8. If we instead allow for a less efficient super Eddington jet, the black hole can grow very quickly to a few 10 to the 7 and then almost stops before starting to grow again. And so we can try to understand how this behavior changes the properties of the system in general. We can measure the star formation rate in the galaxy. You can see here when the two simulations start to differ, there are some differences here, and here you can see for the less efficient jet, a drop in the star formation rate. One might say, okay, but if the jet is less efficient, why is the star formation going down compared to the other case? And the reason is, there are two main reasons. One is that if the jet efficiency is lower, there is a lot of material being accreting by the black hole, so not available for star formation anymore. But at the same time, by this redshift, the black hole has grown a lot. So even if the super Eddington, the jet efficiency is lower, the black hole is so massive that the jet is still very powerful. And indeed, if we look at the maps, I don't have it here, we see that at some point the black hole carves a region of a few hundred parsec in the center of the galaxy because of the jet that interacts with the ISM and pushes the gas away, and the star formation drops down for some time until new gas comes in, and then they realign together at the same value. And you can see here the evolution of the accretion rate of the black hole, the actual measure from the simulation in red, and the smoothed evolution in green. And the blue one is the Eddington accretion rate for the black hole. You can see that in the early phase, the black hole is growing above Eddington, a few times Eddington on average. And then at some point it goes down. This is the drop where the jet has been launched and has carved the central region, and then it goes up again and saturates around the Eddington limit. But it's self-regulated, so we are not imposing that the black hole stops at the Eddington limit. There are some super Eddington, sub-Eddington phases that on average correspond to the Eddington limit. And I leave this here, my conclusions. We have found in the first, the semi-analytic work that we might form heavy seeds in quasar host. Dynamical heating alone might not be sufficient, and synchronized pair might help, but we still more work to understand better how these heavy seeds form. We have introduced a new sub-resolution model that we would like to use for subsequent studies of black hole seed formation. We found that POP3 remnants, black holes still dominate the total mass budget of the galaxy in low mass galaxies at high redshift, and the black holes can stay in the central parsec without wandering around. So they might actually accrete when enough gas mass arrives there. Of course, if the gravitational wave recoil when they merge is not very strong. And this is something we are still missing in the simulation that we would like to include in the future. And then, in order to study the subsequent evolution of high redshift black holes, using cosmological simulation, we have evolved a massive galaxy, finding that it can reproduce quite well the properties of high redshift quasars observed by JWST and ALMA. And we can find that super Eddington phases are plausible and can last for 100 megayears or so in the early phases of black hole accretion. So these might favor black holes to grow above the correlation with the galaxy, with the stellar mass, and then realign only at later time. Thanks.
Time for questions.